Welcome back to physics. Today, I want to extend what we talked about last week, electrostatic forces and methods of charging objects, into some more basic concepts: electric field, electric potential energy, and electric potential. So let's start with an example here to kind of bridge us from electrostatic force into electric field. We have a penny. Pennies today are made of mostly zinc and a little bit of copper. We're going to assume that we have an older penny that is made of entirely copper. That's about 3.1 grams, or 2.3 times 10 to the 22nd atoms. From a periodic table, we know that copper has 22 electrons and 22 protons. First thing we want to do is calculate the number of coulombs of positive charge and the number of coulombs of negative charge. If I start with my number of atoms, we can take that and convert that into a number of charges because each atom has 29 protons. Once we're in a number of protons, we know that one proton has a charge of 1.6 times 10 to the negative 19th coulombs. So when we go across that picket fence, that's going to tell us 106,720 coulombs of protons. If we did the same calculation again for electrons, your numbers are going to be the same. And so then we're going to have 106,720 coulombs worth of electrons. Your only difference is your protons will be that positive charge, your electrons will be that negative charge. We're going to remove all the electrons from the penny, which would be very, very difficult to do. And then we want to separate them and put them at opposite ends of the school. We're going to use the old school building because Google Maps is not updated to the new construction yet. So we've got diagrammed down there the old school building and the measured distance from where the front door was to the back door, 120 meters. We want to calculate the force. So then on the diagram there, we would put Q1 there by the front door, maybe that's our positive charge, and Q2, the negative charge, by the back door. So then plugging into Coulomb's law, okay, Q1, Q2 over R squared, that's going to be 9 times 10 to the 9th, Newton meter squared per Coulomb squared. Each of your charges are the 106,720 coulombs. And then your distance from one charge to the other charge is that 120 meters. So plugging those numbers in, we get 7.12 times 10 to the 15th newtons. They are opposite charges, so they will attract each other. Now let's think about that value for a minute. 7.12 times 10 to the 15th. Well, 10 to the 6th is a million, 10 to the 9th is a billion. 10 to the 12th is a trillion. 10 to the 15th would be a quadrillion. So we have 7.12 times 10 to the 15th, or 7.12 quadrillion newtons of force attracting those two charges to each other. Well, if we were ever to do that, that would have punched a hole straight through the school building as those charges rushed to get to each other. Literally, we would see a lightning bolt, and it would have burned through a brick. It would have burned through whatever was in the way between those two locations. And one of the points I'm trying to make, when you charge an object, you're dealing with a lot of charges, millions, billions, trillions of charges being transferred. But those are only really the outer valence electrons of the atoms. You're never taking all the electrons away from an atom when you're charging an object. It is just those outer shell, but it's still a large quantity. Now, bridging into electric fields, what we've calculated in B is a force, but this is a force acting on a certain amount of charge. If we want to kind of standardize that, if we want to be able to compare it, well, how does that compare to other charges and forces that are applied? Then what we're going to do is take that number of newtons and we're going to divide it by how many coulombs there are. And then we can get a ratio of this number of newtons acting on a single coulomb of charge, and that's a quantity we're going to call an electric field. So then when we take our numbers, 7.12 times 10 to the 15th newtons divided by 106,720 coulombs, then we get 6.67 times 10 to the 10th newtons of force acting on each coulomb of charge. So then, marking up my diagram, if I can get a different color, we'll use pink. That usually shows up. If right there where I put the big pink dot, at that location, due to the other charge, we would have 6.67 times 10 to the 10th newtons of force acting on each coulomb. Well, a coulomb is a lot of charge. Maybe we have a microcoulomb. We can still take this value once it is in newtons per coulomb and set up a proportion and scale that to different smaller or larger amounts of charge once we have that constant. So let's take that and now define that as electric field, or sometimes we'll also attach the word strength there because it is a numerical value for electric field strength. Electric field strength is basically the ratio of the electrostatic force acting on an object at a given location to the amount of charge at that location. More generally, we can say there is an electric field if there is a region where charged objects experience electrostatic forces. By analogy, we've talked about a different field before. We've talked about gravitational fields. And a gravitational field, for example, exists around Earth. So when we have Earth here, we know we have gravity. Near the surface of the Earth, gravity has a value of 9.8 meters per second squared. But then to be able to calculate the gravitational force acting on an object, that would be the object's weight. Then we take that gravitational force. It's equal to mass times gravity. Well, if we solve that equation for gravity, that's a ratio of that gravitational force to the mass of the object. Electric field strength, really, we're basically saying the same thing. The electric field strength, E, is equal to a ratio of the force, but this force is going to be the electrical force, and instead of the mass, it's the charge of the object. So then our electric field strength, just in words, is equal to the ratio of the electric force divided by the charge, the number of newtons of force acting on a coulomb of charge. So your electric field strength, E, is kind of comparable to gravity, just a different kind of field. It's a ratio of the force to the mass. A force acts on a specific object, but then gravity is the same for every object. Similarly, you have electrostatic forces that act on different charged objects, but the value of an electric field at a given location is going to be the same for every charged object. If we consider what Earth's gravitational field would look like, well, everything near the surface of the Earth is attracted to the Earth. So if we wanted to draw a visual diagram, we would draw a bunch of arrows all around Earth pointing directly towards the Earth, and that would show us what that field looks like. Well, similarly, we can diagram electric fields. We got two different kinds of charges here, so then there has to be a sign convention, and the basic way we determine what direction we're going to put those arrows is basically the direction a positive charge will experience a force. So, for example, suppose I have some object here. I have an object and it has a charge of negative Q, whatever that Q may be. If I want to determine what the direction of the electric field is, I'm going to take a little positive test charge, drawing a little positive charge there, and I'm going to imagine this charge at different locations all around my object. So If I draw an arrow, that positive object would be attracted. Anywhere I put it around that negative object, that positive test charge would be attracted. And so our electric field would be a bunch of lines that are just pointing towards that negative object. By comparison, if I had an object here that was positively charged, I would follow the same method. I would take my little positive test charge and I would imagine it at different locations around the object, and then I would draw arrows that represented the direction of the force. Well, a positive test charge would be repelled away. And so my field here would be a bunch of arrows that would point radially outward. Now, let's say I changed my charge and I doubled the amount of charge that was there. Well, that would mean we would have twice as much charge. Positive test charge would experience more forces. We would draw more field lines to represent that field is then stronger. So those arrows are just a way to be able to picture it. And in the investigation you're going to ponder, you will see a little bit more on that in terms of those arrows. So conceptually, I'm just trying to introduce you to the big concepts: electrostatic force and field. They kind of go together. Force is what the object experiences. Field is the overall region around a charged object where it affects other charged objects. I want to throw another pair of concepts at you: electric potential energy and electric potential, and kind of introducing these by thinking of what we've already pondered this year. We have pondered a gravitational potential energy. Gravitational potential energy is the energy associated with an object due to its position in a gravitational field. And we calculated that with mass times gravity times height, m times g times y. Well, electric potential energy is the counterpart, but we're not dealing with objects of mass, we're dealing with objects of charge. So then we would define electric potential energy as the energy associated with an object, specifically a charged object, due to its position in an electric field. So electric potential energy is the same basic idea, it's just a different kind of field. If I have, say, an electric field that is in that direction, and I take a charged object, like my positive object right there, well, the same way that if I had a tennis ball and I released it, it would want to fall towards Earth and follow the gravitational field lines. If I release this positive charged object, it's going to want to move in the direction of those field lines. Well, that would be to the region of lower electric potential energy. If, on the other hand, I moved it against the field, I would be doing work on it and I would increase the electric potential energy. I would give it more energy of position. Now, electric potential energy is useful, but usually when you're dealing with charges, you're not moving a single charge. You're moving millions, billions, trillions. So then we need to introduce the idea of electric potential, which, kind of paralleling it to electric fields, is going to be a ratio. It's going to give us a number that is not only more useful, but used more in the everyday world. We're going to define electric potential as the ratio of the electric potential energy to the charge of the object. So then in symbols, V is your symbol for electric potential. That's going to be equal to electric potential energy, PE, just like we used for gravitational potential energy, but we'll subscript it with an EL for electric, and then charge is a Q. In units, the unit of electric potential is a volt, and that's why the symbol V is used, and a volt is equal to a joule per coulomb. Generalizing out from a joule per coulomb, work is also in joules, And so we can also think of volts as work being done per unit charge. I want to introduce you to the big idea of these concepts because we're going to get into applications with what this means and also applications into circuits. So when you're thinking of electric potential, think of your units of joules per coulomb, work per charge, energy per charge. Now let's take a minute to talk about some examples of volts and exactly what those volts mean. I'm sitting outside now because it's a really nice day outside, and I want to demonstrate what we just talked about with electric potential, which is also called voltage. Remember, we define voltage as a ratio of the potential energy to the charge, or the number of joules per coulomb. So I have a digital multimeter here that will measure voltage or electric potential, and I have a bunch of different batteries. I'm going to take a AA battery here, and let's meter this battery. So I'm going to touch the two contacts. Normally in class I would have a second person holding this, but I will do it on my own here. And when I meter, if you look at the meter there, we're reading about 1.60 volts. 1.60 volts means 1.60 joules per coulomb. So think about a battery. When you put a battery into a circuit, you put a battery in there to, say, light a light bulb or run something in a circuit. What the battery does is inside the battery there are chemicals. It's a chemical reaction that takes place that converts chemical energy into electrical energy to push charges to flow. So if this battery rates 1.6 volts, 1.6 joules per coulomb, that means that it does work to push charges to flow in a circuit. Those charges that flow are able to do 1.6 joules of work for each coulomb of charge that is made to flow in the circuit. So if that's running, say, a light bulb, then you're able to get 1.6 joules of light energy for every coulomb of charge that this battery causes to flow. So when you're thinking about voltage and interpreting it, what you need to think about is whatever the number is in volts, joules per coulomb. If I take a different battery, let's say this battery, and I meter across the two contacts, on our digital multimeter there, we're reading about 8.02 volts. Well, this battery, if you can see it marked on the side there, is a 9-volt battery, which was in our smoke detector just a few minutes ago, but I needed a battery, so I took it out and I'll put it back in a few minutes. So this battery is a little bit older. It's not quite reading 9 volts, it's reading 8.202 volts. So that means when I put this in a circuit, it causes charges to flow, and those flowing charges are able to do 8.02 joules of work for each coulomb of charge that is made to flow. If I take another battery, I did the AA just a minute ago, I'm going to take the AAA battery right now, and if I meter across this one, hopefully without dropping it, so we're reading 1.57 volts. A little bit of fluctuation there. If you can see on the side of the battery here, a AAA battery is rated on the side of it 1.5 volts. A AA battery is rated on the side of it 1.5 volts. A C cell battery is rated on the side of it 1.5 volts. A D cell battery is rated on the side of it. It's a little bit smaller there, harder to see, 1.5 volts. A's, B's, C's, double A's, triple A's, they are all rated exactly the same, 1.5 volts. What you vary in is the amount of chemicals that are in the batteries, okay? And by the different amount of chemicals, you have a chemical reaction that can occur. You still get the same number of joules per coulomb, but if you have more chemicals, you can react more joules or more coulombs of charge. So this battery has more chemicals. It can push more charge, or it might last longer than, say, this battery. In your 9-volt battery, you've got a different chemical reaction going on. This is an alkaline battery as opposed to a dry cell. And so this chemical reaction results in a different amount of joules per coulomb being produced. Electrical outlet. I'm going to take our meter and I'm going to switch the setting over. I'm going to open up our electrical outlet, which is another reason why I sat here, because I'd have easy access to it. These are designed to do this. So I'm going to meter the outlet. When I put the probes in there, we are reading about 121.3 volts, joules per coulomb. 121.3 volts means 121.3 joules of energy per coulomb of charge that is made to flow. So when I plug something in our electrical outlet, it causes charges to flow. Those charges that are flowing have the ability to do 121.4 joules of work for each coulomb of charge that is made to flow. Our battery's got that energy from chemical potential energy, from a chemical reaction occurring. Our outlet leads through the wires, eventually back to the electric company, whereby we produce electrical energy either by hydroelectric, where water is flowing to turn turbines to generate electricity, or we burn fossil fuels like burning coal to boil water into steam, and the steam turns turbines to generate electricity, or not around here but in different places, nuclear energy that we've talked about. A nuclear reaction to boil water into steam to turn turbines to generate electricity. So somewhere work was done on these charges to be able to give them energy, and when you hook up a battery or plug something into an outlet, those charges flow and do work on whatever is in the circuit. So kind of in summary, when you see a number in volts, what you need to think of is joules of energy per coulomb of charge, or joules of work that the flowing charges can do for each coulomb of charge that is made to flow. Ponder physics.